Okay, in this video, I'm going to explain how to do regression by hand. And so where we are is we have determined that we have a significant correlation. You're going to only use a significant correlation to make predictions, because if it's not significant, then it's not going to be a very good predictor. So in class, we'll talk about some of the terminology and the logic of doing this, but the idea here is that we're going to find, and I can show you, we're going to find the line of best fit through our data, and we can use this line to, hence the name linear regression, to make specific predictions, right? And so we have to determine the line of best fit, and we're going to use an equation, right? You might remember from your math education a long time ago that, y is equal to the slope times x plus whatever the y-intercept is. So you may have used slightly different terminology, but we're going to use that linear regression equation. And in this case, our y is whatever we're predicting, right? X is the value that we're going to use to make the predictions. And b is our slope. And we're going to use this statistical equation to determine the slope. So statisticians have already figured out the equation that will give us the slope of the line of best fit. And then a is going to be our y-intercept. And so this is our equation to determine a. So basically, once we determine b and a from our data, we can then substitute them in, and we can use this line to make some predictions. So that's what we're going to focus on in this particular video, and then I'll explain errors of prediction. There's a detailed handout that I'm not going to go too much into in this video, but I'll just sort of give you an overview of it. So what we need to do is we need to determine B given our data set. So we need some entities, and you're going to recognize some of these things that are very similar from a correlation, right? In number of pairs of scores, sum of x, y, sum of x, sum of y, right? And then the sum of x, actually all of this stuff is very similar to the Pearson R, but there's no square root, and then there's, of course, the y term is missing here, but it's very similar. So let's suppose that we have a student, and for each student we have some sort of entrance test score, and we have their first year GPA. And what we're going to do, we assume that they're already been correlated, that these entrance test scores are correlated with freshman GPA, but now we're going to generate a regression equation that we can use to make some more specific predictions. So what we're going to do is, again, here's our x value. I've listed this again. This is very similar to the correlation that we did. Here's the y value, right? Sorry, this is off a little bit. And then we have x squared, so 86 squared, 96 squared, 59 squared, and so on. And when you sum that up, you get the sum of x squared. We don't need y squared, so you don't have to do that. And then x times y is 86 times 2.9, 96 times 3.1, 59 times 2.1, and so on. And then when you sum them up, you're going to get this number of 14, 18.1. So now it's a matter of substituting. So we have 6 number of pairs of scores. Sum of x, y, that was this value here, 14, 18.1. Sum of x, 505. Sum of y, 16.5. Sum of x squared, right? And then sum of x, which was 505. You're going to put that in, and you're going to square that. So then it's reducing. So we reduce, we do the math, and you get 0.02875 is our value for our slope. So that's good. Now we need to calculate the y-intercept, or a. And so here's the formula. And it's pretty simple. It's the mean of our y variable minus the slope times the mean of the x value, or x variable, right? So again, it doesn't matter what you start out by calling x and y, but you're going to use x to predict y, so you want to keep that constant. So let's determine the y average. So essentially, what you're doing is you're summing all these up, 16.5, and then you're dividing by the number of pairs of scores, or 6 in this particular case, and your average is 84.16 for the y mean. And so is 2.75 for the y mean. We do the same thing for the x average. So the x average is 505, right? Summing all that up, dividing by 6, and that x mean is 84.16. So let's put them into the formula. So 2.75 goes here. We calculated the slope in the previous step, and that goes here. And then the x mean which was this value, goes right here. You substitute them down, and now you have a y-intercept of 0.3302. So plug them into our regression equation, right? The y prime, whatever we're predicting, 0.02875 times our x value plus 0.3302. So if you want to use this to make predictions, you substitute your x values in, and you can predict a y value. And that's going to be a good predictor based on this regression equation. By the way, if you wanted to do the opposite, if you wanted to use this to predict x, you'd have to reverse your x and y values and generate a new regression equation. A lot of the relationships, it'll be very similar predictions, but not always. So you'd have to be completely accurate, you'd have to reverse the data and generate a new regression equation. But this regression equation would allow you to use whatever your x variable is to predict your y variable. So let me briefly talk about, now this handout talks about calculating the standard error of estimate for regression. So this is a way to sort of assess if you have two predictors, which one's better. So let's suppose we have their entrance test scores, and this is the same data. And we also have high school GPA, and we're using them to predict our first year GPA. Let's suppose they're both correlated so that we know that there's a good statistical relationship, but now we want to figure out which one's better, right? Well, what you could do is you could generate this thing called the standard error estimate, or really what it is the standard deviation of y, and the dot here means given x. So given that we have x values, what is the variability in y? And so essentially we can generate this, and this text distributes how it explains how you're going to do this in a couple of different ways, showing you how we do this. And we generate it for test scores, and then we're going to generate the standard error of y given x for high school GPA, and we compare the numbers. And in this case, the number for test scores is lower than the number for the high school GPA. So that means we have less errors in prediction using our test scores than high school GPA. As you can see, we're only off 0.11 versus 0.138. So that would mean that the test scores in this particular example is a better predictor because there's less error in our prediction. Remember, our errors are not going to be 100% right all the time. They're going to be off a little bit. And so in this case, this value tells you that this one is a little bit better predictor. And so you can evaluate two different predictors to see which one is better to use.